All right. Today, I would like to write a basic address translation simulation thing. So I recently read chapter 15 of Operating Systems 3 Easy Pieces, um, which is basically starting to look at virtual memory and how that kind of works on the modern system. And I would like to, build a basic simulator. Um, Chapter 15 is like very introductory. It doesn't go through all of the complex ideas of virtual memory yet, but I thought it gives a few assumptions that would make building a simulator a little bit easier. So I thought it'd be a good place to start. It's like a nice foundation, and then as I read a bit more, we could like add to the simulation to add the more complex stuff. So, what does chapter 15 talk about? Basically, I guess we should start with chapter 13, really. The idea of memory for a computer, for a process that's running on the computer, is it's a way for the process to store data, write in data, right? Memory is sort of like a slate for a process to write in data and then read data as well. So that's the point of memory. And memory, we talk about RAM, where you have how much memory available on the system, where each byte in RAM has an address, a sort of location that, that a process can write to and read from. So I guess old systems would allow a process to interact with the legitimate, real, physical addresses of those of that memory, right? Like if you had is this on? Hang on. Okay. If you have like if this big rectangle represents your memory, then you can imagine it's sort of broken into a bunch of bytes, right? Each rectangle is 1 byte, and each of these bytes have a real address associated. So what old systems would allow is for process to write directly to these addresses. So like, if I want to write to address 6, then I would say, access address 6, and it would physically access this memory. There is risk associated with that though. Allowing processes to just access whatever memory addresses they want can allow sort of nefarious processes or a careless programmer to write in the wrong place, read from the wrong place, and then you have problems. So in a way of protecting processes from one another, this idea of virtualizing memory comes out. And so you get this idea of the address space. So this is a very probably something, a sort of diagram that's very typical. Essentially, a process, a process's data is split into certain segments. So you have its instructions or its code, you have the heap, you have the stack, and I think there's also a data segment, but this chapter doesn't really care about that just yet. So you have these different segments, and I guess what kind of happens is as far as the process is concerned, and what we kind of pretend is that this block of memory that the process is owning starts from address 0 and goes till some end address, in this case 16 KB, right? In reality, we call these virtual addresses. These are not real. They are kind of pretend addresses that we as a user or as the process think is what's happening. But under the hood, the operating system knows that this block, this address space, is actually located somewhere else in physical RAM. So what's the point of that? Well, it makes the job easier for the process because, as far as it's concerned, it always starts at address 0 and goes down till some big address number. And there's sort of certain assumptions you can make, but it means that the operating system has more work to do to be able to actually know where the data actually is. So that's where we get to chapter 15, which is sort of the first kind of mechanism that kind of tries to do this. It's called, well, in general, it's called hardware-based address translation, or just address translation. This idea of taking the fake address, the virtual address, and translating into the real location of the data. And I think it's easier to start from the bottom and talk about the actual idea, like the actual technique first. So the thing we're going to be simulating today is hardware-based relocation, dynamic relocation, I think. Yeah, base and bounds is the very specific name for it. So what is that? Basically, imagine this is like the actual RAM. And, before I drew it as like a big rectangle, but here, let's just pretend that this is my real RAM, and then we have like address 0, address 1, address 2, address 3, address 4, etc. Forever, right? Not forever, I shouldn't say forever, but for a while, until like, whatever your final number is. And even though the fake, even though the fake or virtual addresses say, the data starts from 0 to 16, in reality, the data might start from address 4 down to something. So this is the real addresses that are being used. Let's say 4 till 20 or something. So these are the real addresses, whereas the 0 to 16 was like the fake. So what we end up doing is we have what's called a base register. And that remembers the fact that the real address, the starting real address, is 4. And there's also a bounds register, which remembers the size of the address space. In this case, I guess I might have messed this up actually. I think I should say 5. We'll say 4 is here. We'll say it starts at 5. Because I think if it's from 5 to 20, then that's 16 bytes, right? 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. Yeah. I think if it starts at 5 and goes to 20, then I think it's 16 bytes. So this guy tells you the starting physical address. Base register tells you the base register tells you the starting physical address of the actual data, and the base register tells you the size of the address space. So again, the address space is just talking about the block, either in the virtual sense, either this is an address space, but then also, I guess, like, yeah, that's pretty much it. It's the virtual block basically. So it's the size of that. So the bounds register stores the size of the address space. And basically, with these 2 bits of information, if a process ever wants to access one of these bytes, then it's possible for us to check and make sure that the memory access is legal. So for example, from the user's perspective, they might say, so from the user's perspective, it looks like this. It looks like it's going from 0 to 15. This is the address space. Like the block that the user is interfacing with looks like it's going from address 0 to address 15. In reality, it's going from address 5 to 20. Right? But from the user's perspective, so the user might say, I want to access address 3. This is a virtual address. The user can only work with the virtual addresses. So since the user wants to access address 3 in the real block, right, which starts at 5, then goes 6, 7, 8, 9, 10, etc. Address 3 is actually address 8, right? In terms of formula, what you do is you add... Wait, I messed this up. This should say 5. Sorry. I changed this from 4 to 5. My apologies. The base register is 5 because the starting address is 5. So the formula way of figuring out that the translated address 3 should be address 8 is you add the base register to the virtual address you want. So 5 plus 3 gives you 8, which means if the user wants to access address 3, they should actually be accessing address 8, because that's like the corresponding. So this block is basically the same as this block, except this guy is virtual addresses and this is the real hardware addresses. Okay, so the basic formula is, physical address is the virtual address, and you just add the base, because the base basically acts as an offset. The user thinks it's starting here, but in reality, it's starting here. That's the main thing. Okay, cool. And then the only extra thing to understand is, what if the user wants to access like address 16, which is outside? So this would be an illegal access, right? Because if the user has access to addresses 0 to 15, 16 is an illegal thing. How we figure that out is we do the same thing. We add, no, we don't. We check if the virtual address is strictly smaller than the bounds address. So the bounds address, it's pointing, hold up. Yeah, sorry. The bounds register is telling us the size of the address space, right? So 0 to 15 means there's 16 addresses available. So if this guy is greater than or equal to this guy, we know that the access spills outside of the block. So that's what this is saying. If the virtual address is greater than or equal to the bounds register, then there should be an error. In the same vein, like if it tries to access like an address like -1 or something, that's also a problem, but that just means, if it's less than 0, also should have a problem. So if the virtual address is greater than or equal to the bounds address, we have a problem. Or if the virtual address is negative, we also have a problem. So yeah, and that's basically the main idea. By doing that, you're able to translate a virtual address into a real address, and you're able to check for illegal memory accesses. Now, I have severely oversimplified things. What's important to understand is this chapter comes with a set of very strict assumptions. Primarily, those assumptions are a user's address space lies contiguously in physical memory. So I know this roughly, but even if the address space, the virtual address space, looks like this, right, with the code segment and the heap over here and the stack down here, and I think data segments like here or something. But with these segments, even if it looks really nice and neat in here, in reality, in physical memory, it doesn't necessarily have to be quite that neat. It could be a lot more, or a bit more. I don't actually know, but it doesn't have to be that neat. But the assumption says it will be that neat, for now at least. The next one is the size of the address space is small for all processors. So all processors aren't going to use that much memory. Specifically, the address space is small enough to fit in the physical memory size. So that makes me think that there must be a way to virtualize the memory so that a process can use more memory than the physical memory is able to provide or something. But whatever. For now, the assumption is the size of the address space is less than the physical memory size, which again is, I'm assuming, a relatively strong assumption and one that will be relaxed later. And then finally, I think the most this one and this one in particular, I think, are the two important ones for today. the address spaces for all processes are the exact same size, which is definitely something that isn't true in real life, right? In real life, one process might need a lot of memory, one process might use very little memory. So like expecting them to have the exact same size for the address space, that virtual block, is not really that fair. But these are the three assumptions that we will be working with today to make our life a lot easier. And with these three assumptions, if these three assumptions do hold, then the base bounds sort of method or mechanism is a good mechanism to use. But as it notes here, and as the book notes, these assumptions will be relaxed as we go, and we will see sort of why this doesn't work sort of on modern systems. But like I said, I think it's a good foundational place to start. So that's pretty much it for theory. I guess the only other thing is in terms of context switches. So before I was writing, like I wrote up like a MLFQ scheduler, which was for like when a process runs for a little bit and then the CPU decides to interrupt it and start a new one. This idea of a context switch, interrupting one job or process to start another. When that happens, one important thing to do is remember the base and bounds value for the process that you're about to interrupt, because there's only one base register and one bounds register on the CPU, so it can only hold one value at a time. So when one process gets interrupted, its base and bound registers need to be saved elsewhere, and that's called the PCB, the process control block. Each process will have a dedicated process control block, which is basically a struct that stores important information basically about the process. And all those blocks, all those PCBs will be stored in a table, so that shouldn't be too bad. And yeah, that'll just be important so that we can remember things about the process. And so now we'll do this. I've been thinking about this a little bit. My basic plan of attack is I'm going to have sort of some fixed sort of physical memory size. So like I'll be like hash define physical memory as like not equal as like, I don't know, 16 kilobytes or whatever. Sorry, not kilobytes. What is this again? Capital K. Kilo. Wait, hang on. Now I'm annoyed. Kibi, but that's the one. Kibi, yeah. Doesn't really need to know what that is, but for reference, it's this. It's typical unit of measurement for this kind of stuff. Anyway, so we have some fixed size for the physical memory. So we're going to say, for example, there's this many kibibytes of physical memory available, which is a very small number, but that's fine. And then we're going to say, by one of the assumptions, we're going to say each process has a fixed address space size, right? That was one of the assumptions we talked about. So we'll be like hash define fixed address space size is, we'll say like 1 or something. So in our minds, what it looks like is we have this big sort of rectangle of physical memory, which goes from like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 to give us, like, each of these represents 1 KB. So that's basically the physical memory. I think it should go to 15, right? Because it's 16. That makes sense, probably. And then the idea is a process's address space would fit at one per each. One address space would fit on each kibibyte kind of thing. So you could fit a maximum, at least by the numbers I've given, you could fit a maximum of 16 processes. So yeah, we're gonna do something like that. I wanna have a thing where basically the operating system always occupies the 0 KIB to 1 KIB region, because like the operating system is a process and it's the one that's like always running, so it needs space on the physical memory as well. So at least in the book, by convention, it was like always at the very, very top. So this very first top slot will actually be occupied always, in the sense that it just won't be available. But everything else, all these rectangles in here, will be available for use. So there's like 15 left. So max of 16 processes, but one of them's the OS, or the kernel. So that's fun. From there, there's like a couple more things to consider. I need a PCB struct and a PCB table. So the PCB struct will have like a process ID. It'll have like a what else will it have? The base register, and the other one, bounds register. But to be fair, the bounds register, because all of the address spaces have the same size, this value will always be the same. But we'll have it anyway. Process ID, base reg, bounds reg. There's probably other stuff you would normally do, but because I'm really oversimplifying this, we'll probably just need that much. Oh yeah, I'm gonna say no IO. In my MLFQ scheduler, one of the most important things was for there to be IO. Here though, I think IO just adds complexity. It doesn't really add to the exercise, so I'm just gonna say no IO requests. Like the whole dealing with interrupts thing is just gonna be annoying. No IO. We'll also say that the arrival time is the same for everyone, for every process. Arrival time, remember, is like the time at which the process arrives on the system, not necessarily the time it starts on the CPU, because like you can imagine running a program that you wrote, when you punch in enter, that's when it arrived onto the system, but the CPU might not choose, or the OS might not choose that process to run on the CPU straight away. It might have to wait a little bit before it can go. So arrival time is the same for all the processes. And then basically in terms of input, the way I thought I would do this is like, I'll probably use a file, but I mean, I'll use standard input, but I'll probably do this via a file redirect. I'll have, each line in this text, like a text file basically. And basically you'll have a bunch of numbers, and these numbers represent memory accesses, virtual memory accesses. So you can imagine any and every instruction, well, not every instruction, but well, basically every instruction in a process is probably going to access some memory, I'd imagine. I mean, any useful instruction surely would sort of access memory at some point. So these numbers are basically representing those accesses without really specifying what's actually happening in the process, what the process is trying to do. All I care about is knowing what accesses are happening. And then the idea is, so for each line, how do I want to do this? Like construct the process, I guess. So like give it an ID, save the memory accesses, find a free slot in physical memory, and save the base plus bound values. Okay, fantastic. Construct the process. So the ID, save this one, find the free list, find the free slot, and then like add process to the table, I guess. And that should be good enough to I should probably say in a queue for saving the memory accesses, because I want to process them in order. So, and then from there, what I'm thinking is we have this table. Basically, we'll do round robin style scheduling. Just to remind everyone, round robin scheduling is the one with the time slice, where you have like processes like A, B, C. A runs for one time slice, then B runs for another time slice, and then C runs for another time slice. These are all these durations are all equal. 1, 2, 3. These widths, these durations are all equal, and then you basically just go over and over again. I'm purely doing this one because I think it'll be easier to implement. Like, you could argue that I could maybe try to use my MLFQ to really try up the complexity, and maybe even include some IO request stuff in there. But I really just want to focus on like the memory stuff, so I don't want to think too hard about this. Why is this not? I don't want to think too hard about the scheduling. So it looks something like this. Just over and over again until they finish, till all their memory accesses are done. Okay. So time slices the how much time you get before the next guy gets to go. Yeah, that should be pretty much it. And then like the actual functions, so the memory access functions. Will be like given like a particular process and given a address, a virtual address. So given a process and given a virtual address, we'll basically say if VAD is less than 0 or is greater than or equal to the process's bounds, right? Basically just using that same kind of check. We're not gonna crash the program, but we are going to, that'd be bad if we crashed it, we are going to kill the process, which is going to be interesting. What I might do is I might just I might add that to the struct. Alive? Just as a flag, just so I can kill the process pretty easily. And then, in theory, you would free the memory that it's associated with and put it back on the free list. Oh, the free list, okay, hang on. Yeah, if this is true, then do this, and like return. Otherwise, the physical address is equal to v address plus the process's base register, and you can return that. That'll basically be the whole function. Okay, fantastic. So there's that. And then what else do I want? Do I want anything else in particular? Probably not. That should be fine, no? Oh, the free list I said, right? So free list is basically just a structure which stores, I guess, slots of memory. In the context of when we know like that, each address space is going to be this big, a slot will basically be the size of an address space and just all of them. So, we like 1 to 2, 2 to 3, 3 to 4, 4 to 5, like that. Like, I guess 1 is probably better. 1, 2, 3, 4, etc. Up to, what was it, 15? Yeah. Up to 15. And when that happens, then we're like, okay, these are the free slots available. And then every time we see a process and we need to process it in, we'll just say, yeah, you take the most the first available slot, you just take that one and use it. So that would be the vibes. This isn't that hard, but I might make mistakes. It is 12:22. So I don't know why I'm doing this now, but I just wanted to try this. Alright, this shouldn't be hard. I can get this done in an hour, surely. Brave. Okay, so a few hash define. Oh, I probably need like I probably don't even really need, what am I doing? I probably don't really need malloc, to be honest, because maybe I do. Maybe I'll do, I don't know. Because like surely I can do everything on the, whatever, that's fine. Okay, so hash define physical memory size is 16 KIB. And hash define address space size is 1. Num allowed num max processes, okay, hear me out, is equal to 6 is equal to this guy, not equal to, no equals, over this guy minus 1, okay, because basically this tells me how many slots there are, right? 16 slot, each of size 1, so I have 16 available slots. And then because the OS takes out the first one, I'm left with, I have to subtract 1. So this tells me how many user processes or whatever I'm allowed to have, so that way I won't exceed anything. How does standard input work if there's new lines? Like, it's going to be one argument, but it's going to be like quoted. How does this work? If I say like printf I didn't compile. Okay. So if argc is not 2, right? Yeah. Then do a usage thing. Printf usage program, and then memory access list. The memory access list. Sure, let's just say that for now. Okay, cool. And then I need a table. Oh, I need the struct actually. So what did I say? Struct will have, okay, so struct PCB will have the following things, include, what? I don't know. Including an ID. It will have a base register value. It will have a bound register value. And it will have an alive. What? I keep saying hash define. Stood bool. There we go. Alright, and then what I might do is a couple of these. That's wrong. Type def. Wait, what? Oh no, there's no. I'm just guessing right now. I wonder if it's smart to be like type def register. Like, spell type def wrong. And then like maybe instead of integers they should be unsigned integers. Is this dumb? It's a register type. And then instead of ID, it's like unsigned 8-byte integer. 8-byte. 8-bit. An ID type. Is this like really overkill? Is this completely unnecessary? Wait, why do these two things look different? What is happening? Okay. Second pile. Nope. Nope. Oh, is this already a thing? Wait, what? That must be. Hang on. Okay, so not IDT. Proc ID. It's a pretty good name. That's the wrong thing. Also, wait, I used the wrong one. I didn't even use it properly. I spelled clear wrong. Haha, okay. Cool. So, okay, we'll make the array on the stack. We'll say PCB. It's an array of pointers, max processors. We'll call it the proc table, and we'll just not do anything. And then we will pass the input. Wait, no, it's standard input. It's not, I didn't want to do it via this. I didn't want to do it via command line arguments. I want to do it via, or did I? I'm confused now. No, yeah, I want to do it via this command line arguments. So void pass input given the table. I said, yeah, file input in that. It should be a thingy like this. Okay. So how do I read stuff in again? Scanf. Wait. How to read an entire line from standard input in C. Scanf gets like one character or something, right? If I can define a maximum line length, use this one. That's nice. Or until the new line. That sounds like what I want. Although I need a maximum, I need a buffer size. Okay, that's fine. I forgot what I was about to do. If when does return null? Oh, okay. Okay, so char line input line buffer. Well, how big should it be? Surely I don't need more than like 30 characters. Even that sounds like a lot. So a line will look like that, and then while should we do while? But what if it crashes? While f gets, maybe it'll be okay actually. F gets, I need to give the size input line buffer and the file pointer standard input. Well, it's not null. That means we successfully read something in. Then I should construct the memory like pass should I figure out the base and bounds thing here? I guess so. Get the next free memory slot, base and bounds value, figure out base and bounds value, and add the process to the table. I should also have a num processor. Should this be unside integer? What's the difference between this and this? Is it two separate libraries? Like, who's doing this? This is from types versus who's doing that? Also types. They look identical. Okay, I don't think it makes it. I think I just pick one. So while this is not the case, num processes plus pass, or maybe I'll do this at the end actually, because I want the ID to be 0, 1, 2, etc. Okay, assuming that's the case, I should probably construct, I don't need this. Assuming I want to figure out the free list stuff and like figure out the exact memory slot I'm using straight away, I should probably construct the free list. So all the free list is going to look like, it's going to look like the same thing every time. It's going to be 16, it's going to start from address 1 and then go like that over and over again. Am I going to do a linked list? Linked list is like typical for like basic implementation as far as I can tell. But is there a simpler way that means I can code less? No. We'll do doubly linked list struct free memory slot. So it will say whoa. So free mem slot. Next, I want previous as well. Do I need it? Probably not, right? Because all I'm doing is deleting from the head and then inserting to the back. I'm gonna say I don't need it, which might screw me. If I pop from the head, do I insert at the head as well? Or should I insert from the tail? Like, should it be like a proper queue? Or does it matter? I think for my purposes, it really doesn't, especially since the arrival time is the same for everyone. Or maybe I should relax that. Make it so the arrival time can be different times. Otherwise, it's just not that interesting. For now, I think I won't do that. I'll just basically do that. I should also say what address, I guess starting address, and your size. What is your starting address and what is your size? This is basically like the this is basically like the base and bounds. Obviously, you know, this is always going to be the same number, but that's fine. So in terms of I guess this has to be on the heap if I have a separate, like if I say initialize free list, then I'll just do this really scrappily for now. Int I equals 0, I less than max processors. That tells you how many slots I need, right? I'll say free mem slot head equals null if head hasn't been created yet. Maybe I'll say new node first. Free mem slot new malloc size of free mem slot. Yeah, if head is not null, if head is null, sorry, then new next equals, actually this is always going to be true, new next is always going to be head. If head is null, that's still true, but then if head is not, in fact, if I am going to do this backwards, like insert from the back to the front, then head is always going to equal the new, because I'm going backwards. I just need to make sure the size will always be the address space size and the starting address. Okay, so because I've made this very strict in terms of the assumptions, like the formula that I'm thinking is something like this minus I, because this will say there's 15 processes allowed, and the very, the tail node should say 15, and then 14 and 13 and 12 and 11 up to 1, because max processes will be, I will always be less than max processes, so the smallest we'll get is 1, which tracks. So it'll be correct in this case, but what if I was to not make it? What if the address space was 2? You know? Then all of a sudden, I think the math fails. Let me think about this properly. So let's say I have 0 through 15. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, okay. So 0, 1, 2, 3, 4, 5. Should have drawn it closer. In fact, I can do it inside the rectangles. Oh, I miscounted. It was supposed to be 16, right? I must have started counting from 1 and then got confused halfway through. Okay, now the operating system takes so if the address space size is now 2, not 1, I've changed it to make it a bit more, make this better. If it's like this, maybe it is easier to just build it forwards. It'll be easier to go from the back, but actually, hang on. No, this is fine. I can say max, I can say the physical memory size minus the, is it 1 plus I times, okay, so since I'm building it backwards, what's going to happen is I will create a new, the next will go to null, and its new, the starting address will be the physical memory minus 1 times the address size, so it'll be 16 minus 2 will give me 14, which tracks because the very last guy should be these two. Then I'll go again and I will say 16 minus 2 times this guy, so 2 times 2, which is 4. So 16 minus 4 gives me 12, which tracks because it's that guy. And then it'll be 10. And the max processes will be the physical memory will be 7. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Which tracks, because yeah, the only thing that got skipped was the 0, because it's held by the operating system. Okay, cool. I think that's good. So I built it backwards, which was maybe a little bit dumb in hindsight, but that's alright. We adjusted. So news next becomes head becomes new, and then we return head. And then we'll just quickly make the free list. Free list init. list free, given the while current that should work, right? We point the head to where the current is, then we move the current along, and then we free the head. That address is now dead, but that's okay because we moved the current along before we did that. Cool. And that's the only real thing we have to free, right? The actual overall struct. Yeah, everything else is kind of on the stack. Okay, fun times. So then here we can say the free list is equal to init. That works. What? Did I not? Oh, I'm dumb. Okay. So I think passing the input should take in the free list. And then this should have like I'm just thinking now, because if this is a linked list and like the head is continuously being removed from, then the head is now going to be pointing somewhere else, like somewhere down the list. So do I need a double pointer to like make sure the changes get reflected up the call stack, down the call stack? Free mem slot, or I need to like return the head. Free list like get. Free list mem slot. Free list mem slot like that, and then that should be fine, yeah. And basically I'll just say free list, if free list, then free list equals free list next. Do I actually want to free the actual thing? do I want to free the free list? Just, like, not the whole free list, just that particular head struct. Because it's gone now. I might make a struct that's like base bound pair or something. And it's literally just, maybe this can be a base bound pair. Like that. Yeah, it's fine. So the gets, we'll just request a pointer. Your base value should equal the free list, the head's starting address, and the pair's bounds value should equal the free list size. So this is, gotta be careful because this is just referring to the head of the list, not the whole list, but maybe I should call it that. I wonder how much stuff I've broken so far. We can get, and then I also want to insert, so free mem slot, free list, insert. Given this guy, yeah, given a pair, I can just get the values actually, surely, right? Size. Free mem slot new is equal to malloc size of free mem slot new next is equal to the free list head new starting address is equal to starting address new slot. What? No, it's not called, it's just called size, isn't it? Maybe I should call it slot size. I feel like it's a better name. Just a bit more clear what I'm trying to do. Free list head is equal to free list head is equal to this I forgot to say return the new head, so that I can like reset it. Else let's return null for now. I don't know if there's something that will happen, but whatever. Free list head is equal to new, and then return, well, don't have to do that. Return new. This is telling us that the head of the free list head is now new. So I'm inserting, whenever I insert from the head, and whenever I like remove or get, I also remove from the head. So the front of the linked list gets a lot more love, I guess, in the back, but that's alright because our assumptions are strong and my care for detail is not. Okay, so we have this, and then we have this. We can insert. So getting is like deleting. It's like popping off the queue or dequeuing, I guess. But it's not really a queue because I'm also inserting from the front as well. And then freeing. So that should be enough in terms of the free list stuff. Okay, here we go. So hopefully, I need a function that basically gives me the. Do I have a thing for like input line buffer? Void or rather okay, int do I need my dynamic array thing again? maybe I'll instead, because I need to keep track of the number of I'll cheat a little bit. I'll say num memory accesses just so that I know like how to not access outside the array. Basically, I'm going to say pass memory accesses given what should be basically a string. Given an array of characters, given the memory accesses string. How to delimit by white space. There's gotta be something. The string library is pretty good. It alters the string. Wait, what? How? Oops. Subsequent call. What? It's not thread safe. Oh no. Destructive behavior. It alters your source string. If you need to preserve the original text, that's fair enough. But my source string is what? It would be the. Okay. Oh, this gets you the next guy. Oh, wow. That's kind of annoying, but maybe it works? Okay, I guess we can do it like that. That's fine. So basically, I've forgotten everything. Char star current mem address equals null. And then I guess I can take this. Assuming that's pretty good. I mean, new line is kind of weird, but maybe it's good. I don't really know. Char token. I'm like nervous because if there's a new line followed by nothing, because like it'll be like the way I'm thinking about it's gonna be like 1, 3, 5, blah blah, new line. So like if there's a new line here, then will it like try to get another character? I don't really know, but hopefully this will be okay. So current mem axis, I use this guy like that. And then while it's not null, I guess we can just print it for now and then do it again. But what will actually happen is we will convert to an integer via string to long. I think it's that. And then add to an integer array or something, and then do that over and over, and then return. So let me see what happens. So if I basically say do this given the line, and then I basically have this and then go yeah, let's start with like what should be good input and then see what happens. C-line. Oh, I broke everything. Do I need the string? My bad. That's my fault. $112. This is true. Oh, I didn't say input. That didn't work. Did I call this function? I did not. Given the proc table and the free list, compile. Okay, not bad, except that wasn't as helpful as I thought. I don't want a new line, I want to put little these, and then at the end I'll say printf. Like that. That way it will like split them into the actual. That looks pretty good. So 1, 3, 4, 5, 7, 8, 9, 5, 4, blah, 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 blah. Good. What happens if I have an empty line? Does anything bad happen? Sort of. Wait, hang on. So there's an empty line here though as well. There's an empty line here which makes sense, kind of. Why is there an empty 124? What happened? Why is there a... What's a dash V? Let's get rid of the character tag. What happens if I do... Is dash V like space? One of these needs to be space. What the heck? Vertical tab. Ah. Okay. Oh, everything broke. I'm not too sure I understand why there's a like an empty line there. Unless it's because like it must be printing. It printed on negative 124, printed the pipe character, printed the space. And since that was the end of that, because F gets, unless this is more than, I said 30 characters should be enough. Maybe that wasn't true. So could that be what's happened? Interesting. So I think it read in, I don't even know. Wait, so when I said 30 characters and it read in, it read in all of this and then also read in the new line. So that's 30 characters, which means it actually wouldn't have read in the new line, maybe. It would have read in the null terminator or something. And then, okay, whatever. Let's not think about too hard right now. 100 characters. Okay, and then hopefully we say int of, what is it? String too long, given that particular character, the endpoint. Actually, I think I can say like this, and I think I can be like the ampersand of this, and the base is 10. Now, it's a little bit dangerous to cast it into just like this, but that's alright. And then we're gonna say maybe I'll just say finalized addresses or something. So I'll pass in the array instead of constructing it here, and I will say finalized addresses at num accesses plus plus is equal to v, and then do that again, and then keep going, and then hopefully good things happen. And then what I'll do is I'll return the number of accesses. That tells me how long the array is, and then I can store that when I get it. We have that, and then like I need like a number of accesses. We'll say like you can have a maximum of like 30. And I'll error check that just to make sure, just to keep things nice and safe. So u times u, if num accesses is already greater than or equal to the max accesses per process, then we like too many accesses. given to a person. I guess I'll crash out because this is like such a brittle way of doing this, but whatever, it's fine. So the int star finalized addresses is that, and then we're gonna give this array over here. I've spelled finalized wrong. And hopefully that tells me that. And then so I pass the memory, I get the next free memory slot. Why is this wrong? Ah, of course, because I changed the spelling of this. So wait, what does the get do again? So the free list do that, and then get a pair. So I have to say base bound pair. It's a pointer, I assume. And then basically you have to say what do I have to say? I have to make the block BCP, whatever it's called. What's it called? PCB. The current process is equal to what's wrong with that? What? Why didn't it like give me all that? Why isn't it doing the thing? Equals num processes. The base register is equal to the BPP dot base, or whatever it's called, base val. Bounds is equal to BP bounds val. What else is there? This should be true, and this should be whatever the value was. Num accesses alive equals true. This will only be false if like you do something illegal, basically. Okay, so we've done that. Could make this a separate function, to be fair, but for now I'll leave it. This bumps up, and I have to be like proc table at the current proc ID is equal to the current proc. Fantastic. And then I will also say if the num processes is greater than or equal to the max number of processes, then wait, if it's yeah. Hang on, will this work? Yes, it will. Okay, that's fine. Sorry, I thought this would be like a problem, but okay. Okay, what information do I need to pass back? So I've made the little table. The free list, I'm like doing things, which is cool. Wait, do I actually keep track of the... No, I don't. I need to actually know what the memory accesses are. I should just use I should use a dynamic array. My little macro thing. I should have done that because that would have made my life a lot easier. I don't know why I didn't. That was very dumb. Anyway, int current access. The memory accesses I need are the finalized addresses, and the current proc, this value, current access, is I should not. Anyway, it's fine. I'll fix that up later. Should I be printing the number of... I should probably return the number of processes like what I normally do. Fantastic. So then, what's wrong with that? Oh, right, my bad. Okay, so we did all that. I know the number of processes, which is cool because it means that I know like how much of the table is actually filled, so I won't access random things. I need time slice constant, I forgot. We'll say like 3. So in this case, it just means you get 3 memory accesses before we move on to the next guy. Alright. Simulate the stuff. What's this even called again? Simulate basic address translation. I'll just call it simulate. What am I doing? So given given the proc table and given the number of procs and given, I guess I need the free list and I need everything, yeah. Is that it? Do I want a current time value? I guess I could. That's probably good. Current time is equal to 0. Should just be unsigned. How do I? What's my termination condition when all the processes are done, right? Num completed procs, or maybe terminated is better because maybe I'll do something illegal. While I feel I'm gonna really regret this. While num terminated procs is strictly less than num procs total, I'm gonna if I say PCB current running is equal to proc table index 0, that's fine, right? You know, if num processes is equal to 0, if you didn't give any processes, then I'm going to be like no processes given. It's not really an error, but it's also kind of useless. So yeah, well, the number of terminated procs is less than this one. So while we haven't terminated everything yet, we have to go for one time slice and we have to run the memory accesses. So I probably want functions like pick next guy, pick next pick the next process or something. Translate a address, virtual address. Also, you're gonna want to kill a process if necessary. These are functions I'm probably gonna need. None of them will be particularly efficient, but that's alright. Alright, 1 more hour, and I'll get this done. For sure. No doubt in my mind. So, we're gonna wait, is this wrong? Can you declare 2 variables I think this is a thing, no? I feel like I've seen that. Oh, of course. That makes sense, actually. I've seen that. Interesting. So, you want to make sure that I is less than num memory accesses, and you want to make sure that t is less than the time slice. That way you don't, whichever one happens first, plus plus I, plus plus t. So yeah, I should start at whatever current access I index are up to, and t should start at 0. I should go until whichever happens first, and not comma, this should be true and this should be true. So it's going to go for at most one time slice, but we might also just run out of accesses, in which case it terminated. Can I be like current running current access IDX also increases? Can I do that? Is that dumb? Like, that's gonna be happening because whatever I is up to. In fact, I don't need an I. Yeah, wait, hold on. The whole point of this is to... What am I doing? I just need the T thing, and then I can break out early if I need to. Yeah, that's fine. Sorry about that. Okay, one more time. If current running, current IDX is greater than or equal to none memory accesses, then you can basically like terminate this process and then break out. I will add the necessary code for this, but that's the check. That's to make sure that I don't spill past the array. Otherwise, we're pretty comfortable that we're able to do this. At some point, I think I have to increment this as well. Maybe that could be in the for loop. This condition, this increment here. It's fine though. So int the virtual address is equal to current running the memory accesses at current running I think this would have to increase as well. Then we have to translate. If an error is returned, then kill the process. And break out. Else report successful memory access at virtual address, which becomes physical address, which is this guy. Okay. What do I want to do? Let's do the translation stuff first. Let's do that guy. So int so I'll just have a hash define translation error, which I'll set as -1 because there's no way physical address is negative. Int translate address given a virtual address and a PCB process information. So I already wrote this down, didn't I? If the virtual address is less than 0 or the virtual address is greater than or equal to the process bounds, right? So I said then return else this guy plus the base reg. And if I haven't blown everything up, this will be fine, but potentially I have done very poorly. Whoa. What? Virtual address and the current running. If the translated address equals translation error, else process %d accesses virtual address %d, which translates to physical address %d. So current time, current running ID, virtual address, and the physical address. Okay. So that's fine. Kill the process. So here I should say num terminated increases. But I also have to do the action of killing the process, which involves like freeing the memory or whatever. Adding it back to the free list and everything. Okay, kill the process. So maybe free mem slot, because that's going to be adjusted. Maybe terminate process is better. So given probably the proc table I need, right? And this as well probably. And a particular process as well. So proc table process ID I guess I can say alive equals false, I guess. You returned memory is equal to malloc size of free the mem spot returned memory next is equal to the free list head. Hang on, I have an insert function, don't I? Wait, where am I? I've lost everything. Free list insert. Yeah, I don't have to actually do the malloc-ing. Oh, yeah. Hold on. Free list insert, given the head, so free list head, and given the starting address, which would be starting address would be your base register, and your slot size would be your bounds register. That's what it's defined as, right? So you do that, but that returns the adjusted free list head, because I'm inserting at the head for some reason. And then I guess I can return that new head so that I can be like, hey, look, it's pointing somewhere else now. Yeah, and then by doing this, I'm just thinking like it tells me immediately that I don't have to ever look at this process ever again. So given the current running, given the proc table, give the free list head, and say free list head is equal to that. Okay. And then when you get out of here, either you've done the full time slice, or you broke out because you ran out of memory accesses, or you broke out because we killed the process because it tried to do something illegal. So when you break out, or when you leave this for loop, in a for loop you can choose the next guy, next process to run. So that's what this last function is for. So PCB pick next process, given the table, and given like, do I want to give the current running, I guess? The number of processes, I need the size, and so I less than, not 0. If proc table this should say array at I, if you're alive, then return you. And if we don't do any of that, then we should say for int I equals 0, I should be less than the current running ID. So we're going from this. So the first for loop is just going from like wherever the current running is up to the end, and then we're looping back around if necessary. Same kind of vibes. But I don't really need braces here, do I? It reads as one line pretty easily, so I think that's alright. And then if we don't end up picking anything to return up, so current running equals, was it pick next process? Given the proc table, given the num processes, and given current running. And just to clarify, I feel like I am meant to allocate the memory to the processes. I think I cheated a little bit because I think by allocating all the memory like really early, like I allocate the memory before they ever started running on the CPU. I feel like that's a bit cheap. I think it's actually better if like here I said free list get, but I don't think I should have done that. I think I should have, okay, here's what I'll do next time. I'll adjust it if I can. I would say something like, if base reg equals like unset, you know, it can be another like little register unset. Then we can like get then we can do this and then set the things as necessary, you know? I think this is better because like you're not meant to just give all the memory out before things start running, surely that doesn't make sense. So when I used this earlier, I used it over here, but in reality I think this is more fair, and then we do something like this. So if you haven't said it yet, then that's that free list. Nope. Whoa. Current running. Your base reg is equal to BBP, your base value, and your current running bounds reg is equal to your BBP bounds value. And then hopefully that tells us that, you know, if you haven't been run yet, then this register would be still unset. And so, you know, we can do this now. We can do the free listing now, and then we can give you your memory at that point, as opposed to doing it super early, which feels like it's cheating. Just giving too much meta information. Did I get rid of? Yeah, I must have. It's only two. Yeah, it's only 2 instances. Okay. Cool. I have to read this properly because I definitely made mistakes. I just don't know where it would be. Actually, I'm tired. I'll do this later. Let me see if it compiles. Ooh, not bad. Did I say unsigned? Yep. Is there better ways of doing this? Nah, leave it, it's fine. I wonder if this works. Imagine. What? I don't think I ran the simulator. table number procs and the list what? I didn't actually print much. Yeah, but it should have for sure like crashed when it saw that. Ugh. I wonder if I'm actually updating the current time correctly. I might not be. Yeah, anyway, I'm supposed to say printf time process attempted to access virtual address percentage %d. What? Why have I done that? Okay, this will be quite similar. That didn't work at all. I don't even know what I did. I wonder if oh crap. Interesting. Did I not set the Browns reg correctly? Let me see if I can do this cheaply with a print statement. Let me just see. Why is it so slow? Yeah, I'm not actually okay. Fantastic. The bounce reg is meant to be set when which means that this never happened or something. Because all this stuff has to happen. All this has to happen like for the very first guy as well. That might be why that's happening. Okay. I respect that. Yeah, okay. Making the address space size 2 probably was dumb. Because it's not actually, I'm not actually using these units. I basically have 16 bytes of physical memory. Yeah, that makes sense. And then this basically is too big. This is process 0 illegally. Okay, but the thing is, as soon as this happened, process 0 illegally attempted to access. This shouldn't be happening again. Like, what happened after illegally? I've lost everything. Okay, let me get rid of. I think this should be okay now. Hopefully. I have to break out, which means I have to increment current. Whoa, current time has to be incremented. Oh, I segfaulted. I did not expect that. That might be because. How did I segfault from there? Are you serious? Yeah, I figured that wasn't why. This is fair enough. This is good. This is fair enough. Wait, why does it say physical address is -1? Oh, because the... okay, so yeah, it's always going to say -1 because they return -1. I'll just have to say what the virtual address was. My bad. Yeah, don't put the physical address. This makes sense. Ah, because of the empty things, wasn't it? Hang on. Let me get rid of the other one. Oh no, it's not that. Okay, so it's probably to do with the Hang on, why do they all have the same... Oh wait, yeah, that makes sense. Because... because process 0... they all died. Process 0, 1, 2, and 3 all died, so every time you just took the first... you just took the first slot because everyone else was dead. Okay, hang on. Let me make it so that you're only accessing address 0 and 1. I think if you do that, you should be okay. I did not really give myself a whole lot of space. Okay, let me just try that for now. Okay, it's still segfaulting. I'm assuming it's segfaulting because of the freeing as opposed to anything else. So you can see 0, 0, 0 accesses these guys, and then 1, 1, 1 accesses 4, 5, 4 because this guy's still in memory, so it's accessing somewhere else, a different slot. Then 0, 0, 0 again, and then 1, 1, 1, 0, 0, 0. So I think it's working to the extent that good things are happening. Wait, I didn't even call the free function. What? Hold up. Where are you segfaulting? Hang on, let me, oh, I have to do this whole nonsense. Hang on. I have to compile with -G though. Yeah, I know. You. Wait, how do I use the thingy majiggy? Like when I want to run it with. I think I had. My bad. Yeah, there's no what? Fair enough, I think. Hang on. That's the wrong one, isn't it? I want launch normally. I don't know if this is how it works, but if I do this, will this do the thing? Sorry. What do you mean? It does exist. Check it out. It's right there. Oh, I'm dumb. Sorry. The enter program name does not exist. Did that work at all? Or is that the same? What? I'm assuming the input's not being passed through correctly. Yeah. Isn't that what I did? Oh, right. It has to be global. That does make sense to you, though. Alright, one more time. What are we crying about? What? What's making shut? Is it the same kind? Oh, wait, what? Okay, that didn't work. Workspace folder is mini project, and then did I spell it correctly? Input.txt. I don't think my sanitizer works still. I haven't touched this stuff in a while. Oh, it works. Oh, it fixed itself. Best kind of fix. 250. Oh crap. Okay, so that's nulled or something. What's address 4? Or not 4. What is D again? A is 10. B is 12. Address 14. So I've tried to access that, and this was not. That is fair game, actually. That makes a lot of sense. I should have thought of that. I forgot. Basically, if not current running, that indicates that we've ran out of things. You basically break out because it's another indication that there's no more people, there's no more processes to run. I should have realized that. I forgot. There you go. All right. Is that correct? I have no idea, but it's a good start. And the idea is if I change these around, if I make this a lot bigger, make this a lot bigger as well, I should be able to access more memory addresses. This was a bit of a fever dream once. I don't know what just happened. I think I wrote this correctly. Done that. Okay, well, we'll probably finish this off tomorrow.